Hello guys, my name is Bobby Smith. I am the software security manager at Wonderland Investments. My company is looking for a new security firm to protect our Wonderland data. We have selected your company as the best candidate for this position. Can you please tell me about what you have to offer?
We at QuantiBit have developed a strategy to help secure your data at Wonderland LLC. So one problem with the quantum computing that we solve with cryptography is we offer a lot of things, but we're really confident with how our data is transmission. Before being transmitted, data is encrypted using an encryption algorithm or process and a secret key. The secret key, you can choose it. It can be arranged from any numbers or characters. After transmission, data is decrypted by a reversing encryption algorithm using the same secret key. The security of the scheme is based on the premise that the key is distributed only to the legitimate parties. This implies that key transmission is a central problem. So, conventional cryptography techniques rely on mathematical approaches to transmit data. However, security isn't just based on that. It's based on quantum cryptography being that no one is able to eavesdrop on the technology. And what the technology allows is a lot of optical networking with photons where the random key bits are intercepted in a correct manner, which allows and builds your security. And then upon that, its verification is based on the law of quantum physics. Essentially, in practice, quantum cryptography computing allows data encryptation to be from a range of techniques where the strongest is, as simple as zeros and ones to letters and numbers, which really secure data. With this approach, we really believe that from a classical perspective to a quantum perspective, there's a big leap in technology and security. In summary, for just a specific way I believe our company would resolve your problem, quantum cryptography offers long-term security of data being transmission. It's a valuable, it's a peace of mind that you'd be able to secure for a long time in your company.
Wow, that sounds great so far. Okay, so to my understanding, the Heisenberg uncertainty principle is the basis of quantum cryptography. Can you please tell me more?
Well, Mr. Smith, the Heisenberg uncertainty principle is one of the most fundamental theories that contributes to quantum cryptography. This principle states that in a quantum system, only one property of a pair of conjugate properties can be known with certainty. Heisenberg, who was initially referring to the position and momentum of a particle, described how a conceivable measurement of a particle's position would disturb its conjugate property, which is momentum. It is therefore impossible to simultaneously know both properties with certainty. Quantum cryptography can leverage this principle, but generally it uses the polarization of photons on different bases as the conjugate properties in question. Now this is because photons can be exchanged over these fiber optic links, and they are perhaps the most practical quantum systems for transmission between the two parties that are willing and wishing to perform the key exchange.
So here we have in this figure showing how light polarizes in the state of a photon. We define a binary 0 as a polarization of 0 degrees in a rectangular basis of 45 degrees in a diagonal basis. Similarly, a binary of 1 can be 9 degrees in a rectilinear basis of 139 diagonal bases. Thus, a bit can be represented by polarization of photon either one of the two sides, as you can see in the blue and the black of the referencing arrows. So, in the first place, we'll be using Alice trying to communicate to Bob over a quantum channel, for example. Alice begins by choosing a random string of bits. For each bit, Alice will randomly choose a basis. It could be rectangular or it could be diagonal, by which to encode the bit. So she'll transmit a photon for each bit, which corresponds to the polarization, just as described to Bob. For every photon Bob receives, he will measure the photon of polarization by the randomly chosen basis. If for a particular photon, Bob chooses the same basis as Alice, then in principle, Bob should measure the same polarization, and thus he can correctly infer that the bit that Alice intended to send was received. If he chooses the wrong basis, his result will thus lead to a dead end and will be random.
In the second phase, Bob will notify Alice over any insecure channel what basis he used to measure each photon. Alice will report back to Bob on whether he chose the correct basis for each photon. At this point, Alice and Bob will then discard the bits corresponding to the photons, which Bob measured with a different basis. Provided no errors occurred or no one manipulated the photons, Bob and Alice should now be able to have an identical string of bits, which is called a sifted key. The example below shows the bits Alice chose, the basis she encoded them in, the basis Bob used for measurement, and the resulting sifted key after Bob and Alice discarded their bits as just mentioned.
I see now. I believe that quantum cryptography will be a great asset to our company by offering a state-of-the-art security. We will contact you in the near future. I will be looking forward to working with you.